Hello everyone, welcome to this lecture. In the previous lecture, we talked about vibration of single degree of freedom systems with structural damping. In this and the next lecture, we are going to talk about modal analysis of multi-degree of freedom systems, and we are going to consider undamped systems first. So, we are going to talk about modal analysis of multi-degree of freedom undamped systems. So, multi-degree of freedom systems, now they are distinct from the single degree of freedom systems in the sense that multi-degree of freedom systems have more than one mode of vibration, okay, while single degree of freedom system had only one mode of vibration. A multi-degree of system with n degrees of freedom has n modes of vibration. So, that is one difference that is going to occur, and that is going to lead to many new concepts associated with multi-degree of freedom systems. We are also going to talk about undamped systems first. The idea is that some systems in practice can be approximated well by as an undamped system, and then because we can study the natural frequencies, dynamic response of these systems reasonably well by neglecting damping, and hence we are going to focus on undamped systems first. Another inspiration to study undamped systems originates from the consideration that many new ideas like what is eigenvalue problem, modes of vibration, eigenvalues, eigenvectors, normalization of mode shapes, and all these concepts can be introduced more easily using undamped system model, and then we can extend these concepts to damped systems. So, therefore, with this introduction, let us start with free vibration of an undamped system, multi-degree of freedom system. Multi-degree of freedom system. And we are going to consider as an example a 2 degree of freedom system. Because whatever conclusions we draw about 2 degree of freedom system, they can be generalized easily to a multi degree of freedom system with n degrees of freedom. So, let us take a 2 degree of freedom system. So, this is spring, and then we have a mass connected to another spring, connected to another mass, like this. And let us say these masses, they can move freely in the, means they can have motion in the axial direction like this. Let us say this is stiffness K1, this is stiffness K2, this is stiffness K3, mass M1 and mass M2. Also, let the displacement of this mass when this system vibrates is represented by x1, and displacement of mass M2 is represented by x2. And also these masses would also have accelerations associated with them, and let us say x1 double dot is acceleration of mass M1 and x2 double dot is the acceleration of mass M2. So, now we need to write the governing equations. So, what are the governing equations of motion of this system? So, let us use the first thing of course is that let us make free body diagram of each mass, so that we can write equilibrium of that mass. So, if you look at mass m1, so when it is displaced by amount x1 and mass m2 is displaced by amount x2, then the force on this mass would be k1 x1 in this direction. Then we will have a force due to spring k2, and that force would be k2 x2 minus x1, right. So, these are the two forces that are going to mass m1. Similarly, we will have we can for mass m2 we can draw the free body diagram showing the forces that are acting on it. So, this force would be so this force in fact would be opposite to the, so this force would be k3 into x2, and you will have a force on mass m2 which is same as k2 x2 minus x1. Okay. So, here we can assume that if x2 is more than x1, then the spring k2 will be under tension, right, and hence it would try to pull the m1 and m2 masses together, and that is how we have basically obtained the direction of the forces due to spring k2. And then of course, we have this mass accelerating with x1 double dot in this direction and mass m2 accelerating with x2 double dot in this direction, right. And now if you use Newton's law, then we can write down the dynamic equilibrium of mass m1 as m1 x1 double dot is equal to minus k1 x1 plus k2 x2 minus x1, right. And then similarly for mass m2 we can write down m2 x2 double dot is equal to minus k2 x2 minus x1 minus k3 x2. So, if you now shift the terms to the left hand side and take x1 common, then we will have x1, the coefficient of x1 would be k1 plus k2, then we will also have coefficient of x2 and that coefficient would be minus k2. Similarly, the second equation can be rearranged in this manner. So, the coefficient of x1 is going to be minus k2 and then the coefficient of x2 is going to be k2 plus k3, right. So, in this way these are the two equations, and we can now put them in the matrix form. We can write them compactly in this manner. So, if we define the vector of accelerations as x1 double dot and x2 double dot, then this matrix would be m1 naught and 0 m2. Similarly, if we define a matrix of vector of displacements x1 x2, then we get here k1 plus k2 minus k2 minus k2 and k2 plus k3, right. So, and then we can symbolically write this equation as M matrix M vector x double dot plus K and matrix K and vector of displacement x like this. So, you can see this is something we have got mx double dot plus kx is equal to 0, but here all the vectors and matrices are involved as compared to scalar quantities appearing in the equation of motion for a single degree of freedom system. So, you can see in this manner we have got this equations of motion under the free vibration, right. This system is vibrating freely because there are no external forces continuously acting on the system, right, and the system is supposed to have been just disturbed initially or being acted upon by some initial force, like an impact being applied, and then system is left to vibrate on its own, and therefore system vibrates under free vibration. So, therefore, what we see is that now we have the matrices AM here and K. These two matrices basically govern the characterize the equation, and we see that these two matrices, they are symmetric. We can see that they are symmetric, and we also see that the matrix M is a positive definite matrix. Matrix M is always a positive definite matrix, for the reason that if we look at, for example, a quadratic form based on this matrix, right. For example, if you look at the kinetic energy, which is given by half x dot transpose M x dot, right. So, this is in the form of a quadratic term, right. So, it is seen that the kinetic energy is always non-zero, okay. The kinetic energy is always non-zero for a non-zero velocity vector, right. And if so, kinetic energy cannot be ever 0 for a non-zero velocity vector. So, it is always more than it is non-zero if the velocity vector is non-zero, and hence this matrix M is positive definite, okay. If you look at the stiffness matrix, the stiffness matrix can be positive definite or positive semi definite, okay. So, if you look at the quadratic form based on this stiffness matrix, which can be the potential energy, half x transpose k x, which is the potential energy or strain energy, right. Then the potential energy can be 0, right, even if x is non-zero, the vector x is non-zero, still potential energy can be 0. Such a situation would arise when the system has any rigid mode of vibration, when system moves as a rigid body, right, as a rigid system, and so it has any rigid body motion, then although the displacement vector would be non-zero, but the potential energy or strain energy associated with that motion would be 0, and hence this matrix can be positive semi definite. For example, if I take a system like this, if I take a spring mass system, say mass like this, okay. So, this system, if moves like a rigid body, for example, if this has displacement x and if this mass second mass also has same displacement x, then the spring here would be unstretched and there would be no energy stored in the spring. So, it means the strain energy associated with this kind of motion is going to be 0, right. So, therefore, it is possible for the system to have 0 strain energy even when the displacement is non-zero, and hence the stiffness matrix for this system is going to be a positive semi-definite matrix, right. It will be positive semi-definite. But for the system we have considered for our present example, the stiffness matrix is positive definite, because there is no mode of motion in which the two masses can have would lead to a 0 strain energy in the system, the motion of the two masses, and hence in our case the system matrix stiffness matrix is positive definite. So, now question is how do you solve? So, what is the solution of the equations we got, right. So, we should also note that now we have two ordinary differential equations, right. We have two differential equations, right, of second order okay, and they are also coupled, right. They are coupled, they are not independent differential equations, they are mutually dependent in the sense that the two matrices they are not diagonal, right. Although in this case the mass matrix is diagonal, but stiffness matrix is not diagonal, and therefore the two equations we have got, they are coupled. So, they need to be solved simultaneously. We cannot solve only one of them or either of them independently. We need to solve both the equations simultaneously. Now, how to solve the equation? So, let us assume a solution for the differential equation. So, let x is equal to a cos omega t, right. So, if this is going to be the solution of the differential equation, it must satisfy the differential equation. So, let us substitute this into the differential equation, mx double dot plus kx is equal to 0. So, if we substitute this, then what do you get? We get minus m omega square plus k, right, and if I take a common, then we have this result. Okay. And this can also be written as k a is equal to omega square m a. And if we represent this omega square by a variable lambda, then we can write this equation as k a is equal to lambda m a. So, it means that if the assumed solution x is equal to a cos omega t has to be the solution of the free vibration solution of the differential equation, then this equation k a is equal to lambda m a must be satisfied. Okay. And this actually is referred as a generalized eigenvalue problem. Okay, the generalized eigenvalue problem. So, there exists something called a standard eigenvalue problem. Let us go to next page. So, if you look at the standard eigenvalue problem, if I just write in short eigenvalue problem as EVP, then the standard eigenvalue problem in linear algebra is given by, let us say, if I have matrix any matrix B, and so B x is equal to lambda x. So, this is a standard eigenvalue problem. So, here basically B is a matrix which operates on the vector x, and then it produces this linear transformation produces the same vector x multiplied by a scalar lambda, right. So, that is nothing but the eigenvalue problem. Okay. So, in general what may happen is that if B operates on any vector x, it will produce in general a different vector y, right. So, Bx is equal to y, it will produce a different vector y. So, in this case, however, if x is such that when B operates on it, the result is the same vector x multiplied by a scalar lambda, then all such vectors which satisfy this condition are called as eigenvectors of the system, and the corresponding scalars, the lambdas, are called as eigenvalues of the system. But in the present case, we have the generalized eigenvalue problem where we have got, so we have now the generalized eigenvalue problem where the matrix on the right hand side is no longer unity. In the standard eigenvalue problem, the matrix M is unity, right, but here it is not unity. So, therefore, of course, here we have used the vector as A, not x. So, let me write that here. Okay. So, this is the generalized eigenvalue problem. So, solution of this eigenvalue problem leads to eigenvalues, right, that is the values of lambda, and it leads to eigenvectors. Corresponding vectors are the eigenvectors, that is the values of A, right. Then how to solve the eigenvalue problem? So, solution of eigenvalue problem. So, if you look at this, then the solution would correspond to the determinant of this coefficient matrix to be 0. So, we can write eigenvalue problem as k minus lambda m A is equal to 0. So, determinant of this k minus lambda m, this matrix should be equal to 0, right. So, this leads to a polynomial. Okay. So, you need to solve this nth degree polynomial. So, nth degree polynomial lambda needs to be solved in order to find the n eigenvalues, and then we need to substitute this n is any particular eigenvalue back into the eigenvalue problem to find the corresponding eigenvector. So, when that is done, the equations to be solved are homogeneous, okay, and therefore, they do not have unique solution. So, we need to assume one of the elements of the eigenvector and then solve for the remaining eigenvector elements, right, and therefore, the solution of eigenvector is not unique. It is basically a scaled eigenvector, because depending upon the value of the variable you choose for one of the eigenvector elements, the remaining values would accordingly get scaled, right. So, therefore, the eigenvector we get is a scaled eigenvector and it is not a unique vector. So, the eigenvectors we get right, they are scaled vectors, right. The values in them, they are not unique, they can be scaled by any scalar, and the eigenvectors does not change because of that scaling. Now, what do these eigenvalues and eigenvector represent, and what do they represent, or what do they, how they are related to the vibration of the system. So let us take for the case of our 2 degree of freedom system, we will have eigenvalue lambda 1, and let us say the eigenvector is represented by psi 1, right. So this is the first eigenvalue eigenvector pair, eigenvalue eigenvector pair. Similarly, we have lambda 2 as the second eigenvalue, and let us say psi 2 as the second pair. Okay. Now, how these are related with the vibration of the system? So, because we got eigenvalue problem by assuming a solution for the free vibration, these eigenvalues and eigenvectors when substituted back into the assumed solution should give us a equation which satisfies the differential equation, right. So, we had the solution of the free vibration solution was given by A cos omega t, right. So, if I take the first pair, then the since we had lambda 1 was equal to omega, we can write omega lambda 1 as omega 1 square, because lambda was taken as omega square. So, this leads to omega 1 as square root of lambda 1, right. And then we can also replace A by the first eigenvector, right. So, when that is done, so what we get is free vibration solution based on first eigenvalue eigenvector pair, right. So, this is the solution based on the first eigenvalue eigenvector pair, and what we see is that this solution is a harmonic motion, right, because we have the term cos omega 1 t, and omega 1 is the frequency of the motion, and that is why we call this as the natural frequency of this of the vibration, because system is vibrating naturally and the frequency associated should therefore or can be called as natural frequency. Therefore, omega 1 is nothing but the natural frequency. And the psi 1 represents the displacement of different masses in the system, right, and therefore it represents the shape of vibration of the system, right. It represents how the system vibrates, different masses vibrate, and because this eigenvector is can be scaled by any scalar, eigenvector only represents the relative motion of different masses. It does not represent the absolute motion, because it can be scaled by any scalar, and therefore this psi 1 the eigenvector is also called mode shape, okay. And these two quantities together describe the free vibration motion of the system. It represents a particular way, it represents the a particular mode of vibration, right. So, these two quantities represent the a mode of vibration, and we can call this as the first mode of vibration. Let us go to next page. Similarly, if we use the second eigenvalue eigenvector pair, then the motion can be written as where omega 2 is square root of lambda 2, right. So, this represents another configuration or another way in which the system can vibrate freely. So, it can vibrate with omega 2 also, and in that case the vibration of the different masses of the system will be governed by eigenvector 2, right. So, this is called this represents the motion in second mode of vibration. Therefore, what is the summary, right. So, for a 2 degree of freedom system, right, we have two distinct ways in which system can vibrate freely. So, we have two distinct ways the system can vibrate naturally with harmonic motion. Okay, and therefore, we say that there are two principal modes of vibration. Right, and they were obtained by solution of the eigenvalue problem of the system. And these two principal modes, they are associated with natural frequencies and corresponding mode shapes. Right. So, let us take an example to further understand and get an insight of what these eigenvalues and eigenvectors are and what are the corresponding natural frequencies and mode shapes are. So, let us go to next page. So, we take an example. So, for the 2 degree of freedom system we have taken, let us say m1 is equal to m2 is equal to m, that is both the masses are equal to m, and k1 is equal to k2 is equal to k3 is equal to k, that is all the 3 springs have the same stiffness k. So, if that is so, what is going to be the eigenvalue problem? The eigenvalue problem we had was k minus lambda m, right. So, this was the equation for eigenvalue problem, and therefore, in this present case the k would be now k1 plus k2. So, that becomes 2k minus k2, that is then minus k and k2 plus k3, that is again 2k, right, minus lambda, and then the mass matrix was m1, that is m naught, again m2 was also m. So, that is nothing but the mass matrix, and then we have the A here. So, therefore, the determinant of this coefficient matrix must be 0, right. So, we need to take the determinant of 2k minus k 2k, right, minus lambda m 0 m should be equal to 0, right. So, that is something must hold true for the eigenvalue for the corresponding to the eigenvalue problem. So, this determinant would be now simply 2k minus lambda m, right. multiplied by 2k minus lambda m, okay, and then we have minus k square is equal to 0, which means that 2k minus lambda m is equal to k square, which means that 2k minus lambda m is equal to plus minus k. So, if I solve for lambda, then what do I get? Let us say if I take positive sign, then I have lambda is equal to k by m, right, and because we have the natural frequency omega is equal to lambda and square root of lambda m, square root of lambda. Therefore, the first natural frequency, if we represent by omega n1, so n1 subscript n subscript is used to represent the natural frequency. So, omega n1 would be simply equal to under root k by m, and if I take negative sign, then we get lambda is equal to 3k by m, right, which leads to result that omega n2 is equal to under root 3k by m. So, in this way we get the two natural frequencies. Now, to obtain the eigenvectors, we substitute the value of lambda of the eigenvalue into the eigenvalue problem. So, in the present case, what we have got is say 2k minus lambda m. So, let us substitute lambda, right, which in the present case is k by m, okay, into m. Here we have got minus k, and then here we have got minus k, and here we have 2k minus lambda m, which means k by m into m, right, and this is now if I say A1 as the amplitude of first mass, A2 is the amplitude of second mass, then A1, A2, this should be equal to 0. So, what this gives us? This gives us k minus k minus k k A1 A2 equal to 0, right. So, effectively we are having now both these, you can see the equations we get, if you simplify, the equation we get is A1 is equal to A2 from the first, okay, and the second equation also leads to A1 is equal to A2. So, you can see both we get basically two dependent equations. So, effectively we have only one equation which is independent, but there are two unknowns here, A1 and A2. So, this is a result of the fact that the equations we have got, they are homogeneous equations, right. So, that is why they cannot be uniquely solved. So, therefore, we assume, if we assuming say A2 is equal to 1, then A1 also becomes 1, right, and therefore, the eigenvector, if I represent by, let us say, if I represent the eigenvector by psi 1, right. So, in that case this eigenvector would be simply 1 and 1. But if I change the value assumed for A2, then A1 accordingly changes, right, and then it results into a another another vector which basically is a scaled version of the vector just now we got, okay. So, therefore, if I take A2 as say alpha, right, then the A1 also becomes alpha, and this can be written as alpha times 1 1, right. So, we see that just the whole vector gets scaled by the value alpha, a scalar, and that is why we say that the eigenvectors, they are not unique, but they are basically they can be scaled by any scalar, right. And the however, the important thing is that they represent basically the overall pattern of the deflections which different degrees of freedom undergo in a mode of vibration, and that pattern or the shape of the displacement pattern, that does not change, right. The shape remains same, it may get scaled by a scalar, but the shape does not change. Similarly, if we substitute the other eigenvalue, then it can be easily shown that the second eigenvector we get as A1, A2 as 1 minus 1, that is the eigenvector, second eigenvector, right. So, effectively what is happening in the first mode of vibration, if we look at say the first mode of vibration, if we show the motion of the masses, then let us say if I show the motion of the two masses on the y axis. So, I am going to show here x1 and x2, and let us say two masses are here, then what is going to happen? The mass m1 has the same displacement as that of m2, right, like this, okay. And so, when the time progresses, this displacement is going to change like this. So, both masses, they move synchronously, right, they reach to their maximum position, mean position simultaneously in this mode. In fact, in every mode this is going to happen like this. So, it means that in this mode, the both masses, for example, if they move in this direction, they go here and they come back, come to mean position, and they repeat this cycle like this, right. Similarly, if we show the second mode of vibration, right, if you look at the second mode of vibration, the two masses no longer they are in phase, right. In the first mode you can see both masses are in phase. If if one is having a positive displacement, other also has positive displacement. If the first mass has negative displacement, other mass also has negative displacement. But in the second mode, as the mode shape indicates, the two masses, they do not have in phase motion. So, if you again plot this thing, then if the first mass is on one side, the second mass is on the other side. So, this mode of vibration basically is something like this. So, when the oscillation progresses in this mode, then the two masses they trying to come closer to the mean position like this in this mode, and then they go to the other side, and then they reach to the extreme position on the other side. Right. So, this is nothing but the motion in the second mode of vibration. Now, what is the therefore general free vibration solution? General solution under the free vibration. So, if you look at the first mode of vibration, the general solution can be written as x. So, now in addition to, so we have the in the first mode we have the cos omega n1t, right, and then there may be some constant, let us say a1 is the constant, right, arbitrary constants at this, and then the motion if I take say psi 1 sin omega n1t, then that also is a valid solution under the first mode of vibration, and therefore a linear combination of these two motions, the cos and sin motions, is also a free vibration solution in first mode, and therefore the general solution would be obtained by adding the sine term to this, right. So, we get sine omega n1t. So, this is the general motion in the first mode of vibration. Okay. Similarly, in the second mode, the general solution of free vibration can be written as A2. Now, the second eigenvector would govern the displacement pattern, hence psi 2 cos omega n2t plus B2 psi 2 sin omega n2t. Okay. And therefore, the general solution in general would consist of a linear combination of both these motions. So, not only the motion in first mode can is possible, but the motion in second mode is also possible, and these two together also satisfy the differential equation, and hence we combine these two and we can write it like this: AI psi I cos omega n I t plus BI psi I sin omega n I t, right, with I varying from 1 to 2, because there are two modes of vibration. So, this basically gives us the general solution of the free vibration of the system, and here A1 and A2 and B1 and B2, they are arbitrary constants, right, and their values, they depend on how the system was excited and what was the state of the system when the motion started, right. So, their values, they depend upon initial conditions, on the state of the system. And here, this being a second order system, the state vector describing the state requires specifying two variables for each mass, right. For both degrees of freedom, we need to specify two values of, for example, the displacement and velocity to prescribe the state. So, when we know the initial conditions in terms of displacement velocity on both the masses, we can find these arbitrary constants. So, now we can generalize this to a n degree of freedom, multi degree of freedom system. So, generalization to n degree of freedom system. So, what is going to happen for an n degree of freedom system? The mass and stiffness matrices, they will be of order n by n. So, that is one change, right. So, both the matrices, they will be of order n by n. For 2 degree of freedom system, they were of order 2 by 2. But the properties, they would continue to have the same properties, like they would be symmetric, and mass matrix would be positive definite, and mass stiffness matrix would be either positive semi definite or positive definite. And then you will have n eigenvalues and n eigenvectors, right. So, which of course would lead to n natural frequencies and mode shapes. Now, these eigenvectors, they satisfy a very important property, property of orthogonality. So, let us say we have an n degree of freedom system, right, and let us now take rth eigenvalue eigenvector pair. So, for the rth pair of the eigenvalue and eigenvector, we can write the eigenvalue problem as k psi r is equal to lambda r m psi r, right. And for the, let us say if I take another pair of the eigenvalue eigenvector sth pair, then I can write the eigenvalue problem as k psi s is equal to lambda s m psi s, right. And if I now pre-multiply, if I pre-multiply this by psi s transpose, then and then if I also take the transpose of the resulting equation, then what I am going to get. So, if I multiply by pre-multiply by psi s transpose and then take transpose of the resulting equation, then I would get phi r transpose k psi s is equal to lambda r transpose m psi s. So, here this is obtained from the fact that the two matrices are symmetric, right, and then we know the result from the matrix algebra that transpose of product of two matrices is equal to product of the transpose of the second matrix and the transpose of the first matrix. So, and then we pre-multiply the second equation by psi r transpose, and the result is this psi r transpose, sorry, k psi s is equal to lambda s psi r transpose m psi s, right. And now if I subtract these two equations that we obtained after pre-multiplication, then we see that the left hand side involving the stiffness matrix cancels out and we are left with lambda r minus lambda s psi r transpose m psi s is equal to 0, right. And now if r is not equal to s, right, so it means we are having the two modes being different, r and s, and if the eigenvalues are distinct, okay, then we see that the lambda r will not be equal to lambda s, the eigenvalues are distinct, and then what is going to happen is that psi r transpose m psi s should be equal to 0. And so, this is a very important result. It says that the rth and sth eigenvector, they are orthogonal with respect to the mass matrix, okay, because this product psi r transpose m psi s is equal to 0, and then if we substitute this in this result into the equation, then we also get this result that psi r transpose k psi s will also be 0 when r is not equal to s, right. So, it means the our rth and sth eigenvectors are also orthogonal with respect to the stiffness matrix. And if r is equal to s, then these two quantities, they are not going to be they are not going to be 0. Okay. So, psi r transpose m psi r. Okay. So, this is not going to be equal to 0, but would be equal to some scalar. Let us call that as m r, right. And similarly, if for the stiffness matrix also we will have the scalar as k r. So, let us write that on the next page. For the stiffness matrix also, psi r transpose k psi r, again it is not equal to 0, but is going to be equal to some scalar, and let us call that as k r. Okay. So, so these m r and k r. So, let me write the equation for m r again here. Psi r transpose m psi r is not equal to 0, but is going to be equal to m r, and so this is called modal mass, and this is called modal stiffness. We will later on see the implication and physical meaning of modal mass and modal stiffness. Now, is there a relationship between k r and m r? Let us look at the eigenvalue problem again, eigenvalue problem, right, and let us use the rth mode. So, we have k psi r is equal to lambda r m psi r, right. So, this is the eigenvalue problem in terms of rth mode, and if we pre-multiply this by psi r, then we get psi r transpose k psi r lambda r psi r transpose m psi r, right. And from the orthogonality properties, just now we got the result that psi r transpose k psi r is nothing but modal stiffness k r lambda r, and psi r transpose m psi r is nothing but modal mass m r, and therefore, we get the result that rth eigenvalue is nothing but the ratio of modal stiffness and modal mass, right. And because we also have the result that omega n r, that is the rth natural frequency, is equal to the square root of the rth eigenvalue, we get the result that omega n r is equal to square root of omega k r upon m r, right. So, this is a very important result, that the modal mass and modal stiffness, they basically together, they are related through eigenvalue, right. Now, let us also define what is called as modal matrix. Modal matrix is basically the matrix of all mode shapes, right, all matrix of all eigenvectors. So, if I define a matrix psi which is of order n by n, then we can basically take the first eigenvector as the first column of this matrix, second eigenvector as the second column of this matrix, and in this manner if I take all these eigenvectors together, the nth eigenvectors, then basically this gives us a matrix of order n by n, where each column is an eigenvector, right. So, this matrix is nothing but modal matrix, or we can also call it eigenvector matrix. Okay. And so, now we can also express orthogonality properties in terms of eigenvector matrix. We can write these properties through a compact expression. Each of them we can write through a compact expression, right. So, therefore, we can say that psi transpose m psi, right. So, what is going to be the result of this? So, only because each two distinct eigenvectors, they are orthogonal, the off diagonal elements of this matrix on the right hand side is going to be 0, while the diagonal elements are going to represent the modal masses. So, this matrix is going to be we are going to have say MR1, that is the first modal stiffness, then MR2 and MRN. Okay. So, that is going to be the and then off diagonal elements are going to be 0 like this. So, we can simply say that it is a diagonal matrix of modal masses. And similarly, in terms of stiffness matrix, we are going to have a diagonal matrix of modal stiffnesses. So, KR1, KR2, this goes up to KRN, and off diagonal elements would be 0, and we can represent this as a diagonal matrix of modal stiffnesses, right. So, that is how the orthogonality properties can be expressed in compact form, and these orthogonality properties play a very vital role in modal analysis, because they are going to allow us to decouple the equations of differential equations, right. That is something we will see later. Let us also talk about the normalization of these eigenvectors. So, as we said, the eigenvectors, right, if I take any particular eigenvector, it's basically has an arbitrary scaling factor, right. It has an associated with a scaling factor. So, the question is that can we choose a specific method of scaling this eigenvector. So, the first method to scale this eigenvector could be like we say that the maximum element in this eigenvector is unity. So, maximum element in the eigenvector is unity. So, to scale it in this manner, what we do is that we check which is the maximum element and divide the whole eigenvector by that element. So, which basically forces the maximum element to occupy unity value, and all the remaining elements occupy a value less than that, right. The other method that can be used is to have the length of the eigenvector as unity, length of the eigenvector is unity. So, we can therefore find the Euclidean norm of the eigenvector and divide the vector by that. Okay. So, that will ensure that the Euclidean length of the new vector is 1. Another method that is used, which is widely used in modal analysis, is mass normalization. So, mass normalization of eigenvectors. So, in this we divide the each eigenvector by square root of the corresponding modal mass. So, if I have the eigenvector psi r, then we divide this eigenvector by square root of the corresponding modal mass. So, this gives us a new vector, let us represented by phi, right. So, what is the result of this way of normalization? If we look at the orthogonality of the with respect to the new vector phi r transpose say m phi, then this would be equal to, basically it will lead to a unit modal mass, right. So, when that is done, so this can be easily verified by substituting replacing phi r with psi r upon square root of m r, and then using the orthogonality property result, right, for psi r. So, this leads to a unit modal mass. So, an eigenvector when it is mass normalized will have a unit modal mass, and that is basically the idea behind mass normalized eigenvectors, and therefore, phi r is also referred as a mass normalized eigenvector. And therefore, if we now express the orthogonality property in terms of mass normalized eigenvectors, then if I define again the eigenvector matrix using the mass normalized eigenvectors, then I have the matrix phi phi. So, phi transpose m phi. Now, this would become now a unity matrix, phi transpose m phi, and in terms of the stiffness matrix, I have the result that this would be equal to phi transpose k phi would be equal to the matrix of eigenvalues, right, which means that we will have eigenvalue of the different modes on the diagonal like this lambda n, and off diagonal elements should be 0. So, that is nothing but the eigenvalue matrix. So, these are the results based on the mass normalized eigenvectors. So, I think now we can stop here and we will continue beyond this point in the next lecture. Thank you.